So I'm here to talk about how we'd use the different cable sag values that Jay previously talked about. So it's just a continuation of the cable forces and which cable force goes where. So based on what I have pulled up here on the screen, we have the hoisting sag value, the dead load sag value, and the live load sag value. And so we use these to then figure out the distance from, we're able to go to the other part of the manual to equation 5.1 and 5.3. They're the same, just with different H values. So I'm just going to talk and look at this one for a second. But so the F value is the vertical distance between the lowest point of the cable in that sag position and the lower tower saddle. So you need to pay attention on your bridge for which side has the lower saddle, handrail, walkway, same thing. But typically you'll want to pay attention to the walkway first, but you'll also need the handrail saddles. So what we do is so I'm here to talk about the different places we're going to use this, right? So the hoisting value isn't really part of the calculations, but it's really important for construction. The dead load is really important for our freeboard requirement, and then the live load will tell you, gives us our maximum load that we check the actual bridge abutments, anchors, and cable capacity for. So we'll go through that really quickly. So basically what the process is. So let's start with the hoisting sag. We will plug in our H values. So right now, the example I'm going on is this bridge here. It's a 24.2 meter span bridge. When I multiply that by our hoisting sag of 4.6%, I get this value down here at the bottom of the layout drawing, and that's our 1.1 meters. And then I will go to the manual to equation 5.3, and I'm going to plug that in for H hoist, so our 1.1. I'll use our delta H that I've previously calculated from the survey. This bridge in particular, delta H, is 26.5 centimeters. And then that gives me an F value of 0.98 meters from the right abutment. And so that's not dimensioned up here because it's not a final condition and we don't want it to be confusing, but you need this value for when you're setting sag, even when you're hoisting the cables. So when you're ready to put the cables on the bridge, or even the day before, depending on how things are going, you'll want this value on this 0.98 value on the drawing. You'll want to go out to your tower, bring out like a level, and measure down 0.98 meters exactly. And when you're lifting the cables up above the river, trying to tighten them up, you want to make sure that you go above that line because the cables are going to stretch. And then once the cables are stretched and it's sag set day, you don't want to have to lift the cables even more because that's a pain. You just want to be able to drop them. And so that's why that's really important. Another aspect of that is that you'll need 0.98 meters for the walkway and the handrail cables, so you'll really need 2 spray painted lines. And then you can also have 4 spray painted lines, and you can find where that low point is on the higher tower, because depending on the topography of the site, you might have a better vantage point on one side, because I mean, you're in the auto level and you want to make the auto level, you want to make your eye point level with the bottom of the cable. And so depending on which side you're able to look at, because you'll want to look at the line and then you'll want to like be able to pan to look at the cable. So that's why it's important to provide that low point from the right and the left, or the high and the low side. The low side's easy, it's just the equation 5.3. The high side is equation 5.3 plus delta H, because that's just how much it's sagging plus how much of difference there is between the two saddles. So if that doesn't make sense, please feel free to ask questions. And so that's what we do with hoisting. For the dead sag, so 5%, we multiply that by a 24.2 span bridge. That gets us to 1.21 meters. And then we go back and we can look at equation 5.1, same deal, just plug in 1.21 instead, and now that gave me the value of 108 centimeters right here. So here on this drawing on the layout page, zoom in, I'm looking for the distance between my saddle, so where my cable sits right here, and the lowest point of the cable. It's 108. And then I also know and that value is all based on your span and your delta H. And now you have to make sure that that value, so now you have to finagle your bridge to make sure that the distance between the lowest point of the cable and the high water level is more than 3 meters. So that's where you can see here on the drawing of, I know from my saddle to the low point it's 108, and then based on the survey, I know my freeboard is actually going to be 321.4 centimeters, which the minimum requirement is 3 meters. So there we go. So that's what we show that on this drawing because that's the final condition. Typically in industry with engineering drawings, you don't show construction planning, you just show the final condition, and then we have the note down here for hoisting that helps you get there, basically. So it's really important that this value, this F distance from saddle to low point for dead load should not be equal to the F values that you put down here for hoisting. So just make sure that doesn't happen. And then the last value is our live load sag. And so that doesn't go anywhere in the drawings, but that is what we use for the cables. So that's what we use in order to figure out the cable tension that Jay's gone over, and that's what we use. So like live load is the highest load the bridge is ever gonna see. That's when theoretically all the people are on it, or there's like motorcycles or different livestock. And so we want, as an engineer, you want to guess, have an educational guess on like the highest load the bridge could ever see. And that's what we want to design the cable capacity for, the abutment overturning, the anchor uplift, and sliding. And so that just goes into your calculations. That doesn't go anywhere here. If you're wondering why we don't use that for freeboard as well, if we put freeboard at the 6.1% sag of live load, it changes our, well, so sorry, if we put our freeboard at the 6.1% load, it jacks up the loads like crazy and makes the bridges really like unfeasible. They're not feasible to build. It makes the abutments a lot larger and unnecessary. And so by engineering judgment, we've decided that when freeboard's a really big problem, it's a huge storm event. And so likely people aren't gonna be crossing the bridge. They'll only have to cross if it's an emergency. Hopefully they're like sheltering in place because there's crazy weather happening. But that's the thought process behind that. The last thing I'll say though is that this course is modeled based off of the standard sag values that are in the manual, so the 4.65% and 6.1%. There's a chance that when you're assigned your bridge, you'll be given custom sag values that us on the technical committee will give you that'll allow for a more efficient design.